Good afternoon, everyone. My name is Nashr El Auliya, and today I'll be going over my senior design project from the College of Engineering. So, maritime shipping holds enormous significance in today's globalized economy, but unfortunately, it is still one of the biggest contributors to the global greenhouse gas emissions, contributing about 3% globally. And that's actually a pretty significant number, considering how many sectors and how many contributors there are. Now, with that fact in mind, the challenge becomes, can we lower the adverse environmental effects of maritime shipping while simultaneously keeping up with modern demands? This is the challenge posed to us by Professor Anthony Lin of the College of Engineering when he tasked us to design and develop a supplementary or even standalone propulsion system to be equipped on cargo ships, paying special attention to fuel efficiency, sailing speed, and budget. To put things a little bit into perspective, I'm going to go over a little bit of, the inspirations that we drew from for our solution. So out on the market right now, there's obviously a handful of competitors that are trying to do the same thing. But the two that we really liked are listed over, I've put them up over here. And the reason that we really liked these two and we wanted to draw inspiration from them is because, one, if you look at Michelin's example here, they sport inflatable sails. So those sails can actually be deflated and then stowed away. And then Bar Technologies, we really liked how the sail on the wind wings can change its curvature, albeit to a limited amount. And so these two qualities are qualities that we are drawing inspiration from. Now, in order to understand how our solution works, there are three important terms to understand. The first one is lift. Severely boiled down, birds stay afloat and planes fly because of lift. What exactly is lift? Well, lift simply refers to the force produced due to a difference in pressure between the top and bottom surfaces of an airfoil, right? So if you look at the symmetrical airfoil over there, right, the symmetry of its geometry makes it so that, well, in that particular setting, no lift is produced, right? And so how would we produce lift in that situation? Well, if we change the angle at which a symmetrical airfoil meets the wind, suddenly this difference in pressure now changes. There's more pressure buildup on the bottom surface and lift is now produced, right? This angle is known as the angle of attack. Now the question is, can we achieve the same level of lift at a lower angle of attack? The answer is yes, and you do that using cambered airfoils. What does camber mean? Well, camber really just means how curved the airfoil is relative to it being symmetrical, right? Now, a really important thing to keep in mind about lift is that it will always act perpendicular to the direction of the wind. Now, in aerospace applications, this is great. That's exactly what you want. You want your plane to stay up. But unfortunately, in sailing, it gets a little bit more complicated. You want to be able to modulate the direction you're headed. You want to be able to change headings. And what this effectively means is that you can't sail straight into the wind. And this means we have to take a detour. This detour, or the process of taking this detour, is known as tacking in sailing. I bring this up because making the process of tacking simpler, more predictable, and more manageable is hopefully one of the desired outcomes of the solution that we are proposing. Now, our project team consists of 6 students split into 2 sub-teams, but today I'll be talking about the sub-team that I worked on, the algorithm. Before we get to the algorithm, I just want to go over the final prototype that we came up with. And as you can see, the sail that we've designed has the ability to change its curvature, just like the Bar Technologies solution, using the multi-panel design that we've came up with. And each panel is individually actuated by these small stepper motors on the bottom at each joint. And then, as you can see as well, our sail can be retracted or stowed away when needed. And so my part in this project is figuring out how we can get the curvature of the panel, but also the curvature of the panels, but also the orientation of the sail to adapt and react to the ambient wind conditions that cargo ships would be seeing out in the ocean. The curvature of the panels themselves, as I mentioned, will be actuated using the small stepper motors, but the orientation of the sail will be actuated by rotating the mast using a medium stepper motor instead. So how did our prototype fare? Well, the medium motor was able to change the orientation of the sail by rotating the mast. That was pretty simple, and we achieved that. But the small motors struggled to rotate the panels against its own weight, bearing down on the joints, right? And another point to keep in mind is that we used stepper motors, and so they're not locationally aware, right? They don't know what angle they've been rotated to. And so this leads to a couple of action steps that we've had to take. First of all, we are, as of today at least, we're in the process of switching out the small stepper motors for small servo motors instead, because they have been rated at a higher torque, and so we're hoping that would be able to overcome the weight on the joints, but also because they're locationally aware, and we found that this locational awareness is really important in being able to mimic the camber profiles that we want. Additionally, we would have to implement a calibration protocol for the medium motor in rotating the masts. That's already in progress as we try to implement limit switches. And then finally, we have to determine if any appreciable lift force is produced from our prototype. Preliminary tests show promising results, but we haven't been able to reach a full-scale evaluation yet, at which point, if we do, we would be able to then perform an aerodynamic similarity analysis to basically say, okay, does our model translate from this table-sized prototype to a whole cargo ship out in the ocean? We believe that's either something we might be able to touch on by the end of the semester, or we could also hand it off to the next team that picks up our project. With that, I conclude my presentation, and I'll be taking questions now. Thank you very much.
Oh, that was a great presentation. Thank you so much.
Thank you so much.
As someone who's shipped over 15,000 containers through the course of my career, I had a great deal of interest. Curious, I love what you presented. I can imagine the servo motors being very helpful, and you're on a great track. Did you consider propulsion systems at all, including green hydrogen or other possibilities? Was that ever a consideration?
Well, very early on in the project, our advisor did say you could look at additional complementary propulsion systems, but he did specifically ask for a sail. Professor Lin is, he's an avid sailing hobbyist, as we've come to find out, and so the main goal was to produce a sail to be equipped on cargo ships. And the biggest reason why is that I think ultimately the direction that we were headed is the complete elimination of fuel. Right. I understand that hydrogen fuel is a lot more greener than the diesel fuel typically used in cargo ships, but I think ultimately what we were looking for is this complete elimination of fuel.
Again, really nice presentation.
Thank you so much.
I have two questions. So the first one is very engineering. Your sail has, if maybe it would help to go back to the picture. You have, I don't know, there's eight different sections there?
Yeah, those are just different. You're talking about the panels?
Mm-hmm. In the leftmost graphic, I can see 8 up and down sections.
Yeah,
and I'm just
panels.
wondering how you arrive at the number of 8. I can see that 2 doesn't give much flexibility and 100 maybe is too many. Was that something you optimized, or would that come later?
Well, to be completely honest with you, the decision of having 8 panels was outside my scope. I mentioned earlier that there were 2 sub-teams. The aerodynamic sail design team arrived at that number after their simulations.
Okay, and then just more broadly, you've emphasized the big role that the fuel to push these ships causes for greenhouse warming. But on the other hand, ships have lots of other needs, And I wonder if the optimum solution may have to be a combination of wind and solar. So, for example, just to turn the lights on the boat, that's not going to be, if you don't have batteries to store wind energy, which I'm not aware of, I think it has to be a combination. And I was just wondering if y'all talked about that at all.
Yeah, sure. To be completely honest, we ultimately did not address the entire ecosystem of the ship. But that certainly does sound something, a lot more plausible than just leaving it as is. But we did, very, very explicitly define the boundaries of the project early on in that, okay, can we find a way to substitute or at the very least complement the current onboard propulsion system on cargo ships? Yes, there are other needs on a ship, but the big point that we really want to drive home is that the biggest contributor to the greenhouse emissions comes from the engines of these ships. And so the big question is, how do we use that engine less?
Agreed. And obviously a lot fewer oil spills, we can hope.
Yeah, oh yeah. Thank you.
All right, thank you so much for the presentation. This is awesome, and this is shape-shifting.
Yeah.
Awesome to see. I have a few questions. I'm actually just curious about how you are approaching things. So the first thing is, why you went for motors instead of, say, linear actuators? Is there a specific reason? It seems to me that the range of motion of each panel, angle-wise, is pretty limited. So I would think that when you scale up, linear actuators like pneumatic actuators would be maybe easier to implement.
Well, to be honest with you, we chose motors as opposed to linear actuators for the purpose of making prototyping a lot easier. And so there are two aspects of the project, right? The design of the sail itself, and then I said algorithm, but I feel like probably a more accurate way of describing what I worked on is more so the control system, right? The control regime of how we plan to control this, this array of panels, right? And so the idea was to find a way to make the prototype built as efficiently as simply as possible, and then we can focus on, okay, what are the shapes for the sails that we want? And then on the control end, it's like, okay, what exactly is the decision tree, or what exactly is the algorithm? What exactly is the chain of process that we want to happen? And so that's, using motors just made that a lot more simpler. Because we just, at least on the controls end, what we really wanted was just like, okay, if X wind angle is red and Y wind speed is red, what does that mean for the lift? How do we react to that? And the easiest way to react to it and actuate that reaction as simply as possible is using motors.
Right. And related to that, talking about the control problem, I teach embedded systems, so this is kind of in my wheelbase. I was wondering, right? So one way to talk about lift, or at least to measure, is via differential pressure, right? So you could measure where you have high pressure versus low, and then sort of like react to that gradient and try to maximize the differential.
Yeah.
Have you thought in this case about instrumenting this with pedal probes and pressure sensors, differential pressure sensors, like they do on aircraft to understand the?
Yeah. Right. Well, that was actually a problem that we encountered midway this semester, because early at the end I mentioned determining whether appreciable lift is achieved or not, and we had to figure out, there were a bunch of options that we were looking at. Do we put a load cell on the mast and see how much tension or compression, depending on the direction, is being experienced by the load cell? Is there any way to do exactly like what you said? Or if there's some other method out there, right? Unfortunately, we haven't been able to solve that problem yet. And to be completely frank, we were heavily banking on the College of Engineering's wind tunnel to be available for us to use. But unfortunately, the wind tunnel, it's not so much the size, but their load cell, their sting, we call it, where you can mount your foil or whatever, it's not exactly in operational condition right now. And so that's really one of the obstacles that we have to figure out.
Still pretty inspiring. Thank you so much.
Thank you so much.
All right, and I think me and Rithvik can say thank you all. We are actually going to hand it off to Laurel and Alana for.
Yep, thanks.